Right. Magnetism will not be on the final. It'll be on a take-home test. Yeah. Okay, so if we go into course material and assignments, I've put this stuff under week 11. I don't know if we're in week 11 or not. I think we are. But I have in here in week 11, this is a Faraday simulation. If you want to play with it a little bit, kind of do an at-home lab, this is pretty cool because what we're going to show is that Ampere showed that if I have a current in a wire, I created a magnetic field. And the reverse is also true. If I have a moving magnetic field, which is what we're going to see today, if I have a moving magnetic field, such as a bar magnet, and I put it through wires, look what's happened. I create a current in the wire. So a moving magnet can create a current. Current, which is moving electricity, can create a magnetic field. So magnetism and electricity are linked. Hopefully on Wednesday, I will do my Lenz's Law tube, demonstration because my tube happens to be over in Tonkawa. And I didn't go through Tonkawa this morning to get here, so I didn't pick it up to do it. But we'll do the Lenz's Law tube demonstration, which is kind of cool, that you can actually see that the magnetic field causes an electric current, which causes a magnetic field, and we get a impedance down the way. And so we'll get our third electrical component that we use in electric circuits. So if I take and move through here, I can get the magnetic field, and the key is it's a moving magnetic field, all right? The key here is that it's a moving magnetic field. And that's what's also going to cause the auroras, because I get the magnetic field is going to trap those charged particles. Those charged particles get excited in the magnetic field, and we're going to get an electrical discharge, and we get the pretty lights that are out there. So you can actually start to see the deflection if I'm moving the magnet. So you do have this simulation that you guys can play with. You can flip the bar, and you can change the direction of the current, which is kind of fun. You can change what kind of fields that you get in here. You can play with it. You can add more rings. You can play with fewer rings. It's kind of fun to play with. So I've given you the simulation. Down here on this one, motors and generators, this is a really good, I use a lot of stuff from the University of North Sydney. Because the physicist down there has really good demonstration pieces, really good GIFs to be able to look at different aspects. So he has really good things about how a DC motor is generated, how a DC generator works. And this right here is our slip ring. This is actually a really specialized piece of equipment. This slip ring that you've got, where you've got two brushes that are attached to it that will actually collect the current that's being generated. So if we think of those windmills out there that we're watching, this is the vital piece for electricity generation in those windmills. It's the vital piece for any turbine to help us get that electric generation. So I've got the DC motor piece in here. You can actually play these, that you can see the torque and the bounce, whether it's a DC motor or a generator or an AC one. So I've given you this link to this page so that you can actually kind of work through it, and it gives you the explanation, the difference between a motor and a generator, and then there's the alternator, and it shows you with these slip rings, and you can play and look at the voltage as it's going through the slip rings and how you'll get the current and the voltage being applied through the system. So that's in what I've done. And then we've talked about paramagnets and electromagnets and building simple motors. And this one uses the wire, this wire here with the magnets across. But you can also buy the really cool, if you go to Hobby Lobby, Or like Walmart, you can find the world's simplest electric motor that uses a a D battery in it, and we have them in the labs. So those are kind of fun, so you can actually kind of see and play with it. So that's there for you guys. And then let's see, this is another YouTube. So we're gonna look at my favoritist one first. So we're gonna start with this one, and you may want to hit the lights. I'm going to wait until the lights are hit there, and then I'm going to get the sound up here. Okay.
On top is a 1 kilogram aluminum plate.
So we hear this noise. What's that noise?
The vibration of the cavity, because it's vibrating at 2 times the density of the stomach of this one.
Whoa! Whoa! How does it do that?
To find out, I've come to the place where it all started, the Royal Institution in London.
This is the key to Faraday's magnetic lamp.
Amazing that lock, don't worry. Well, the 18th century also became a storeroom, which is why it survived, and it survived intact, all the joinery, perpetual magnet, exactly the same as Faraday.
So this is exactly as Faraday would have had.
That's right, yeah.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electric hardware shop and ask for a meters to insulated wire. You had to insulate the wire as it went. And so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction. He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the 2 coils repel each other when the current is induced. And that's due to the interaction of their magnetic fields. Which brings us back to this. Through the bottom coil, we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of the second coil, we're using the aluminum plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates.
How awesome is that?
This current is not only good for levitating the plate, it can also make light bulbs glow.
Oh, thank you. Whoa! That is cool. Can I put it there?
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Thank you. Check out how hot this plate is. Oh, that is nuts. Is this your favorite demo?
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction.
So the magnetic current generates, or the magnetic field, the moving magnetic field generates an electric current. The electric current generates a magnetic field. So we end up getting that going back and forth. So if I go back, I want to go back. Okay, this is another one looking at the law of induction. And it's the more simple, basic laboratory setup. Let's see. Oh, I've got it as full on as it can go, so. So you can play with that one as well. So that kind of gives you a feel for, and so that link, this is the Faraday's lab video, that's the induction video, there's the simulator, there's the motors and generators. And one of the things that I had promised right before break, or our test time, was I was going to do a calculation related to the field induced by the magnetic field induced by an electric current in a wire. So I'm going to switch over here. So hopefully you can see the document camera. You can see the document camera over there?
Yes.
All right. All right. So if I take two wires, okay, if I take two wires, hang on, I'm going to set up this to make sure I've got everything I want on the screen. All right. So I'm going to set up a wire, and this wire has got a current going in that direction. And I've got another wire, and I've got a current going in that direction. So if I use my right-hand rule, the current's going to generate a magnetic field going into the paper this way. This one is going to generate a magnetic field going into the paper this way. So in between these two, the magnetic field net is going to equal the magnetic field due to wire 1, we'll call that wire 1, and wire 2, we'll call that wire 2. Now I've got this as a magnitude, okay, because we're going to say your book may say into the paper is negative, but in this case we're just going to look at the magnitude, and because these two wires are generating magnetic field, and I'm using the right-hand rule, my thumb goes along the wire with the current, my fingers are going into the page, thumb goes along the wires with the current, my fingers going into the page, those are going to be additive. And if you go back and you look at what we did on the slides and what's in your book, the magnitude of the magnetic field is going to equal our permittivity of free space divided by 2 pi times the current divided by the distance r. So if we have these two wires, and the wire that we have has a current of 5 amps, and just to remind you, mu is equal to 4 pi times 10 to the minus 7, which makes this factor right here, although our book doesn't do it, but a lot of other books will do this. They'll take this 4 pi times 10 to the minus 7, divide by 2 pi. Pi's cancel, the 2's cancel. I get this term right here is going to equal 2 times 10 to the minus 7. So depending on what book you have, depending on what other things, excuse me, another one's probably coming. That depending on what we have, this constant here, sometimes you'll just see it as 2 times 10 to the minus 7. So if you're using Chegg, or you're using tutor.com, or you're using another online tutor, a lot of times they'll just give you this 2 times 10 to the minus 7 factor, but they won't tell you where it's coming from. And it's coming from the fact that I've got this permittivity of free space divided by 2 pi, and going through this analysis right here, I get my 2 times 10 to the 7th. So you'll see a lot of things. They'll show you an example, and there's all of a sudden there's just this 2 times 10 to the minus 7th, and you're going, where the heck did that come from? Well, that's where it came from. So if I'm wanting to look at this magnetic field, anywhere within this spot, it's going to be additive. So if I look at this and I say the distance between these two wires is d, and I want to look at it at a point that's halfway in between, so d over 2. I want to look at it as a point halfway in between. I can rewrite this total thing as B net is going to equal, and I can factor out this mu 2 pi term, the current in wire 1 divided by its distance, which is gonna be D divided by 2, plus the current in wire 2 divided by its distance, D divided by 2. And that way I can simplify this as mu 2 pi, and this becomes 2I1 divided by the distance plus 2I2 divided by the distance. And if my distance happens to be D is equal to 0.1 meter, I can just plug in my numbers, and I'm going to get 2 times 10 to the minus 7. And this becomes 4 times my current, which was 5 amps, divided by my distance, which was 0.10 meters. And if I do this, I end up with, and I put it in the calculator, end up with 40 microtesla. So you can actually do the nice additive portion of it. And you can play with this all the way around. All right? You can play with this in a variety of different ways, because I can now take those 2 wires and do a variety of different additions. So let's do one. So if I have my wire going this way, and I have this wire going this way, so the current for this, the current's going to create anywhere on this side, my current's going to be going into the page. Anywhere on this side, my fingers are going to curl around, and it's going to be coming out of the page. So I'm going to use this as wire 1 in black. So now I'm going to do wire 2, and I'm going to actually use red to show it. So if I do wire 2, my fingers are going along the current, my fingers are curling into the page. So anything on this side of wire 2 is going to go into the page, but anything on this side of wire 2 is going to come out of the page. So now if I want to find the field at this point here, so we're going to say the distance between these two, D, is equal to 0.1 meter. And now the distance over here, let's say it's equal to 0.15 meters. If I'm going to solve for my magnetic field, it's still going to be B net is equal to B1 plus B2. And if I say into the page is negative, and I say out of the page is positive, okay? So into the page is negative, out of the page is positive. I'm going to do this one. I'm still going to have the mu divided by 2 pi, but this is going to be negative I1, and my distance now from this wire to this point is going to be 0.25 meters. This one is coming out of the page, so I'm going to be additive. I'm going to put on a positive, whatever the current is in 2, but it's going to be at 0.15 meters. And then I can just do the arithmetic. So if I1, the magnitude of I1, the magnitude of I2 is equal to 5 amps, I now can just plug in my 5 amps and work the problem. So no matter how I put in these currents in the system, I can work it the same way. Now, what happens if the current is in the same direction? Okay, so if the current's in the same direction, we'll do the same kind of color coding. So for this one, my fingers are going into the page. So over here, it's always going to be positive, or going into the board. Coming over here, it's always going to come out of the board. But this one's going to get a little more tricky, because this one will go into the board over here, but it'll come out of the board over here, and it'll be out of the board over here. This one will still be in the board over here. I'm going to have a point in between these two where I'll have essentially no magnetic field because they're going to cancel each other out if the current, if I1 is equal to I2 in terms of current. So you could start to play with that kind of a thing and look at the magnetic field no matter how far away you are. So looking at that, I'm going to come back to the computer here just a second. I have also given you a link on the computer because I thought it was a really cool paper, a paper on field exposures. So if I go over here and get this paper on field exposures, there are the common magnetic fields associated with electrical appliances. And these are in inches, and the actual values are in milligauss. Remember, a 10,000 Gauss magnet is equal to a 1 Tesla magnet, or vice versa. These are in milligauss. So if I'm dealing with power lines, I've got some where at the center line between power lines and residential magnetic sources, you can actually play with and look at how these things are affecting the fields. And these, I believe, are measured distances. So you can actually kind of go through and look at where things are and look at the epidemiological studies and all of that good stuff. And this is a paper from the USDA. But I just thought it was a really cool table to see what the magnetic fields were associated with the electric current into a particular object. So you've got access to this this page. So that gets you a couple problems to play with, because I promised we would do that, and hopefully next Wednesday I can play with some more problems so you guys can actually see it. But we're going to actually cover some material here to get us where we're going. So this is Faraday's experiment. He had an iron ring. He had 2 wire coils circulating around the device. And when he flipped the switch, because when he flipped the switch, he had a changing electric current. So that changing electric current induced a magnetic field into the ring. The magnetic field in the ring was a changing magnetic field, which induced the current. So the magnetic field creates a current, the current creates a magnetic field. That's why we can build electromagnets. Permanent magnets are made of ferrous materials, so they're usually iron-based. A lodestone is a naturally occurring magnet, but we can actually use an electric field to generate and build a magnet. And you guys have played with that, right? Has everybody made the compass needle, taking a sewing needle and floated it on a cork and played with it? You know, you can get everything to line up and you can make your own little magnet. So we've played with those. So we've been able to demonstrate that. So what's happening? And going back to what we did with electric fields, we know that electric fields have field lines. We can draw those pictures. We've seen the magnetic field because we can draw the field lines using iron shavings. And we can generate that magnetic field those magnetic field lines. But now if I take a loop of wire and I move that loop of wire inside my magnetic field, I've got that flux. So remember when we did Gauss's law associated with flux, and we used an area, we used this good old thing, this right here, but we had an E at the end. I can get a flux through my loop of wire. That's the magnetic field times the area. But again, I have to do that mathematics where I have to take into account, am I perpendicular to the magnetic field? Am I at some angle to the magnetic field? And if I do that, that's going to generate that flux through the magnetic field. So I'm going to get that flux. So I can calculate it just the same way we did with the electric field, except for the magnetic field, it's B. The electric field was E. And so we can look at it that way. So we get our maximum when we're perpendicular, and we get nothing when we're parallel. So I get my maximum when I'm perpendicular, and I get nothing when I'm parallel. So we can have those same things. So we've demonstrated this. You've seen this little experiment. As I move that bar magnet through a loop, I'm going to get a deflection. The real trick now is, what direction does the current go? And it's going to depend on the movement. And that's where Lenz's law comes in, is to help us figure out where that movement is. So I can get my law of induction, and this is why we saw, and this E is my electromotive force. Remember, we talked about how electromotive force is going to be related to voltage, and it's what's moving the electrons or forcing the electrons to move. It's going to be related to how many turns in my loop, because we saw that in that second video. If I have one loop, it's only going to have a certain strength. If I have 2 loops, it's going to be more. If I have 3 loops, it's going to be even more. But it's related to this change in flux with respect to time. And this, from a history point of view, is very, very important. Because what happened to us is my electric field didn't have to change with respect to time. My magnetic field, or the electromotive force associated with my magnetic field, has a time component to it. And that's going to become really important when I start building my circuits, because we saw with a capacitor, we had a time lag as the capacitor filled, right? We saw that it took it a little while for it to fill. Resistors were instantaneous. We saw the effect on current. With a resistor, as soon as we hit the switch, we didn't see any deflection. It just was instantaneous. But when I had that capacitor in the system, I had a little bit of time lag associated with it. Well, when I have an inductor in the system, I'm going to see a time lag as well. And so when we do an AC circuit, we're going to have to really take into account this changing time associated with the changing magnetic field. So that's our electromotive force. So we got our flux. And so Lenz's law says the current caused by the induced EMF travels in the direction that creates a magnetic field with a flux opposing the change in the original flux through the current. It's kind of complicated, but you have to kind of sit through and think about it. And when you'll see that opposing portion of it, that you're trying to figure out which direction the current is going. So we want to kind of look at that Lenz's law and getting that. But this is the key part right here, is I also get a change in time. So if I have my current and put my thumb along the current, rotate my fingers, it'll go through the magnetic field. I'm going to get the induced magnetic field, and I'm going to be able to get where my current is. So if I have a wire, it's going to do this. So there's my wire. My current's going to go in there. So we've used our right-hand rule, laying our thumb along this, which is going to induce a magnetic field around there. So now I've got induced a magnetic field, but now the induced current counters the positive magnetic flux. So this current is going to go around the square loop this way. And you got to kind of play with it. You got to kind of get your fingers on there and go, okay, I can kind of sit there and look at that. And this is what's going to help do maglev trains, because it's going to push the magnetic field away, which is going to help us drive. So by how we click on the magnets on a maglev system is really going to help propel our train forward, or a monorail forward. And that's going to give us that piece. So we can do the induced current. So if I'm moving my current this way, I'm going to induce a current. If I'm moving my magnet this way, I'm going to induce a current that way. So I'm going to get the magnetic current. The induced current produces a counter flux. So I'm moving this. The current is going to go the opposite direction, or the magnetic field that this current induces goes the opposite direction. So we're going to see a kind of a resistance to it. So this is the magnetic field generated by the current. This is the magnet generating the current. And so I'm going to get this to oppose the motion of the magnet. So you've got to kind of play with how these currents are induced. So now we can make electromagnets and we can move things through. So I get my electromagnet, it's going to form a magnetic field. I flip the switch, I'm going to get a current that goes the other direction, and then when I open, the current flips back. So just like what you saw with movement of the bar magnet, I'm going to see the same thing by doing it with an electromagnet. And we can play with those. And that's what, so those little toys that you see where somebody flips the switch and the magnets will bounce off, this is what's happening. It's exactly what's happening. I'm getting an opposing magnetic field. Or a lot of times some of those toys will cause the magnet to flip. You'll get to see the magnet flip. So we can do this. What's kind of cool is we can use this to our advantage. So circuit breakers are doing this. So if I've got a current and all of a sudden I sense I have a current, I've got a little magnet in here, and if the current exceeds a certain point, it's going to trip the breaker, because it's going to cause enough repulsion that trips the breaker, and we know we see the switch, the flip. So we can actually use this to make a device. It helps us with ground fault interrupters, so we can make sure that we don't have a problem with our hand tools and get shocked, because that's a real problem, because we don't want to get shocked. So it works to our advantage. So we get ground fault interrupters that helps us. So if we see a surge or a change or a short, we can have those work. It works for amplifiers. So we can have it make our amplifiers, so we get pickups on guitars, so we get lots of cool things. And it does for monitoring systems. I think one of the homework problems, at least in the old text, has a magnetic band around a person, and they're monitoring the chest rising and falling. And because the chest rising and falling changes the magnetic field, I get a change in current, and I can monitor a breath. The other application for this, think of my loop, okay? If I have a current, right, that's running around in a loop, and I take a car, which is a big iron object, and I drive it across a loop of wire, the loop of wire is going to get a change in its magnetic field, which is going to cause a change in the current, which tells the traffic signal that I've got a car parked at the stoplight. So you've got induction rings that are out at in intersections to help give a signal to change the car light. So that's one of those things that we get so practical application. The other practical application is that we can get the magnet to move. Okay, we can get a magnet to move, and so we can actually get that motional EMF to cause the bar. So if I have a wire across here, I can get a magnet to start moving or have motion across the magnetic field. So the force that's going to cause the motion is related to the charge that's running through the bar or the wire times its velocity, okay, times the magnetic field. That's the force that's going to be moving. And we know from my electric field, and now you can see the electric field's related to the magnetic field. The magnetic field's related to the electric field, because I can actually look at the force that's on the electron. And there it is. There, we've had this way back when in our electric field force. Here's our magnetic field force. And the charge that's moving through the wire is the same charge. So my electric field is equal to the velocity times the magnetic field. Or my magnetic field is equal to the electric field divided by the velocity. So these two things are related. Electric field is related to the magnetic field is related to the electric field. And that ultimately, that fact right there is going to give us the electromagnetic spectrum, and it's going to give us light. And it's going to give us a photon, because photons are strange beasts. But we can work through it. So my change in voltage, if we go back and look at my change in voltage, That's the electric field times the length. I can put the length in here, and I can look at my change in voltage both ways. And I can actually look at how this little bar is going to move, because if I've got my current going through the resistor, how this bar is going to move down the rails is going to be related to the current in the system, and it's going to go counterclockwise if I'm coming I think I've got it backwards. I'm going into the paper here, so we've got it backwards. So we can get that motion, and you could actually say, all right, there's my flux. My flux is equal to my magnetic field because I'm perpendicular times the area, and my area is my length times my change in x, right? So there's my area, and now I can get the electromotive force is related to my change in flux divided by change in time. I can rederive this, that my change in x with respect to time is my velocity that's moving us down. And now I've got my current is equal to my voltage divided by my resistance. And now my voltage, which is this right here, is equal to my magnetic field times the length times the velocity. And I can look at the current that's going through the system. And I can now calculate the velocity of my magnet if I know the resistance and the current that I'm putting through it, and I know the magnetic field that I'm in. I can play with things. Which gets us to generators. Because now, if I do something with mechanical work to force my loop to go around, so think about if I have a loop, and I've got it on a crank, I can crank it around, which means if I'm cranking it around inside the magnetic field, that change in my current is going to change in my magnetic field. I'm going to generate a current, and I can actually generate electricity. And so we can get a generator. So if I do my slip rings, and we were just talking about these slip rings on my generator, if I can rotate this loop of wire between two magnets, I'm going to generate a change in voltage. And this will give me what we call alternating current. I can do direct current as well by how I connect these slip rings, but I'm actually going to get a generator. So we can calculate, there's my electromotive force that's causing it to move. We can do this as perpendicular. My velocity is perpendicular here. But remember, my velocity, if I'm doing something that's spinning, is related to the radius times my angular frequency of how it's spinning. So now I'm spinning my little loop. I can have this go through, and this is my A. There's my A over 2. And I've got my sine of the angle. So I can get my electric motive force for when I'm working with a generator to look just like this, just walking through the equations. And I can calculate my electric motive force that's happening, and I can actually, and then if I have multiple turns, which is what we do, we have lots of multiple turns, I can actually get how that refers back to how that is spinning through my system. And that's a generator. Motors, I'm going to get work out of. Generators, I'm getting current out of. But motors work on the same type of principle that we end up with. And there's my max, because the maximum is going to be when this is equal to 1, and that's where my maximum is going to come into play. So I get my generator. So I get this nice part, I get my slip rings, we can work there. I'm going to stop there because people are glazing over, and we'll come back to the back EMF when we actually see, when we're doing inductors on Wednesday. We'll work a couple of more problems, and we'll be good. So if you haven't got your test emailed to me, make sure you do. I'm trying to gather up all the tests so I can get them all graded and get everything done. Yeah. Oh, that's fine. That's fine. The only thing I can take it from a home email or anything. What I can't do is I can't send you a grade to a non-NOC email. You know, we can talk back and forth, but I just can't send you what your grade is via a non-NOC email. You should be fine. Yeah, I'll take it Blackboard, email, whatever, but I know people were having trouble, so I'll take it by the end of the day. You guys have any questions over there in Tonkawa, even though I can't see you? I guess we're good.